Stagnation temperature and stagnation enthalpy. Suppose that our steady flow control volume is a set of streamline. If you are just saying like these are just a constant streamline and passing through a blunt object over here somewhere. Or in other word, if I'm saying like let's assume like we have got an object, a bullet kind of an object, or an aeroplane actually flowing into a constant streamline. Um, so we are having two initial condition, two condition. Um, Initial condition when the streamline is somewhere a little bit far away from the object, and the final point when the streamline just hit the blunt object itself. So these streamlines are stationary in space, as we are saying, like there's a constant streamline, there's a steady flow streamline. So they are stationary in space. So there will be no external work done of on a fluid as it is actually flowing. Another word, what I'm saying, like let's suppose like these streamline are not actually constant, and there is actually something actually a pressure which is actually coming from this side of the streamline or this side of, so there would be actually some external work on this object itself, and the object would be moving due to the work done. The assumption is actually there is actually a steady flow constant streamline. That's it. And then also assume like there is no heat transfer into and out of the system. The object is actually not leaving some heat out of the system, and it is actually not even getting some heat into the system. So there is two condition into the system itself. There is no external work done, so the work done component is zero, and there is no heat transfer to the system, so there the heat transfer component is zero as well. Moving to the above equation, the steady flow energy equation, so the heat transfer is zero, and for the steady flow streamline, the work done was actually equal to, their work done again is equal to zero. So the above equation or the steady flow energy equation would be something equal to like this thing. Also assuming like the object itself is not positioning or not changing its position, there is no actually z change in the z or potential energy. So we are assuming like this part of the system is also zero, equal to zero, as the mass is also constant. So we will be ignoring this part as well. So we are, the steady flow energy equation, the above steady flow energy equation is now equal to this, which is actually the enthalpy component and the kinetic energy component. The enthalpy component at the initial and the kinetic energy component at the initial as well. Enthalpy for the ideal gas equation, which is actually enthalpy H is equal to Cp delta T, if you remember from the last lecture. So now Cpt2 minus C2 C square by 2, what we call it as a kinetic energy, and CPT1 plus, actually sorry, not that's plus again, plus C1 square by 2 for the kinetic energy component. For the stagnation point, actually, what we call, what is actually stagnation point? The stagnation point is when actually the air or any fluid just hit the nose or the blunt object or state 2. When it hit the state 2 point, imagine the at that particular instant the velocity would become zero. So that means like this component, which is actually kinetic energy component, would become zero, and that temperature at which at that point would be now called as the stagnation point now. So that means like when this component is zero, Cp T, now it is actually stagnation temperature, is equal to now Cp T1, which is actually initial condition, plus C1 square by 2 now. Just divide by Cp this will gone, and then we will be having this one now. So this is actually the component, or this is the stagnation temperature. So what is actually stagnation temperature? The stagnation temperature is the temperature that the fluid would reach if it was brought to the zero speed by the steady adiabatic process with no external work done. So that means, like, when we hit the object at point 2, the speed becomes 0. Initially we were assuming that the process was steady flow, and we were also assuming that the process was adiabatic with no external work done. So now the proper definition of the stagnation temperature would be: the stagnation temperature is the temperature at which the fluid would reach if it brought it at a zero speed by a steady adiabatic process with no external work done. Note that for the any steady adiabatic flow with no external stagnation temperature is constant when we need it actually, and when we need the stagnation temperature and stagnation pressure. So let's suppose we have got the same kind of an object, or let's suppose an aeroplane, and that's actually flying in the steady flow airspace. So we are interested in the temperature at the surface of the aeroplane, or we are interested in the pressure at the surface of the aeroplane. So we are saying, like, this would be the stagnation temperature and stagnation pressure of the object, of the object on its surface. It is definitely of the prime importance. So it is convenient to define the stagnation enthalpy as well, and stagnation enthalpy would be equal to this one from the above equation. And if you're writing the steady flow energy equation in terms of stagnation enthalpy, you can actually write it like this as well. For the quasi-static adiabatic process, you have already done in your term exam as well. You have derived these equation. For the stagnation pressure, you can derive this equation. We are not supposed to derive this equation, but yes, for the stagnation pressure, our stagnation pressure, our equation would something look like this, where m is actually the Mach number. Mach number is equal to C by A. Please check your book for more further detail. The stagnation pressure is the pressure that the fluid would reach if it is brought to zero speed adiabatic quasi-static process with no external work done. So an area of common confusion over here is the frame dependence of the stagnation quantities. The stagnation temperature and stagnation pressure are the condition in which the fluid would reach if it was brought to zero speed, and that is actually relative to the some reference frame. For example, if you are moving, if an object is moving in a space actually, and a fluid is actually hit the object at that point, so obviously at that particular instant actually, the velocity of both the object and the fluid is relative to each other is zero, and that's what we are saying, like, when it is actually brought to a zero condition. Depending on the speed of the reference frame, the stagnation quantity will take different value. So yes, if it is actually moving at different speed and it is hitting at different speed, so obviously we are not talking about the relative zero speed, and we will be talking about different values. Steady flow energy equation in terms of stagnation enthalpy, we have already derived the equation above equation in terms of enthalpy, and yes, we might be using when we are looking at the nozzles or the jets examples in the next few courses.